This is a presentation about horizontal control. Control surveying is very important in surveying because it provides a set of points, or we call it a network of points, that works like as a reference for our works, engineering works or other surveying activities. This control surveying, it has two parts, either the horizontal control or the vertical control. In the horizontal control, we will be doing positions in the plane, horizontal plane, as eastings and northings, while in the vertical control we are providing what we used to call benchmarks, and they are points with known elevation. Usually the horizontal and vertical control points, they have fundamentally different points because everyone works in a different way, or let's say is established in a different way. And but these are nowadays, because of the GNSS or the GPS, we have now points that can serve as a vertical and horizontal control. So the purpose of horizontal control is to establish precise relative coordinates in the horizontal plane, easting and northing. So we have points, we want to use them as a reference points in the horizontal plane, what we call horizontal control points, and we need to find their easting and northing, their horizontal coordinates, before we can give it to others, so they will use it as a reference. So in general, when we want to do a horizontal control surveying, either we'll do it to establish a new horizontal control network in an area that doesn't have it, or if we have it and we do not have it dense enough, so we have it to increase the number of horizontal control points, and this is what we call densification. Once established, the horizontal control network or the horizontal control system is considered a public utility that all they can share and they can use. If we do not have this utility in a certain area, that will raise the cost, because the surveyors have to go for faraway places to get the control and reference that area, especially when we are surveying within a city. Two things to consider when we are doing a horizontal control network is that once we are building a, for example, second order network, then we have to rely on a first order network. We cannot build a second order network based on third order points. Also, the control points or the control horizontal control should always be available for the surveyors, so they can use it whenever they want. That means it should be dense enough so that that's to find it anywhere that is needed. In an urban environment, as you know, there are a lot of obstacles from the commercial and the density of the city. That's why mostly the sighting distance will be for the point will be between 100 and 200 meters. So the instrument is somewhere it can look in either direction and can sight from 1 to 200 meters. And now that will make that the total distance between the points, so between the instrument and the points it is 1 to 200, but between the points it will be between 200 to 400 meters. Also, for the purpose of reducing the influence of centering error of the instrument and the targets, the sighting distance or the distance between the points should not be more than 100 meters. That means we should always use short sights. When it comes to the solution of the horizontal control network, we must always have the whole city covered with a uniform, simultaneously adjusted network. Why is that? So we can keep the standards of accuracy the same all over the city. Although this seems to be very, very difficult, but still we have to achieve it either as a whole or as pieces. One example is that maybe we will do part of the city this year, but we will do the second part or other parts in the future. That's why we do not have the readings for the whole city at once, and that's why we have to do the processing at different periods. And to do that, mostly we will do for the whole city, we will do a higher order horizontal control network, and then we will be densifying each part by itself, but depending on that uniform higher order network. And in general, as we said, the higher order control points should be available to surveyors to use them or to encourage them to use that higher order points in their reference works. So what is the purpose of horizontal control? Is that we want to find the easting and northing precisely of a set of points, and then later we will use these points as a reference. We have many methods to achieve that. Some of them they are old, some of them they are new. The change in technology, actually it is driving which method to use more and which method to use less. From these methods we have traversing, triangulation, trilateration, resection, intersection, and GNSS satellite positioning. In the coming few slides, we will introduce you to these methods, and then we will start detailing each method by itself and the way to do the solutions. Mainly, we will be doing the requirements, the range that is covered by each one or favored for each method, and then the measurements required and how to solve that method. And of course, as we said, there are solution methods that they were old methods without computers or powerful calculators, but now we have everything like computer software and methods that they need computer power, and that's why this is the game player. Very, very, very important game player is that the technology that we have now. So let's go for these brief descriptions. First method is the traversing. It is a horizontal control method that we at the end we will be calculating the easting and northing of the stations that we choose, and this kind of horizontal control surveying, it will serve small to mid-size areas. As you can see here, we have the traverses can be across polygons, it can be across links, but either way we have to do the measurements, which are all the angles and all at all the stations and all the course distances, so all angles and all course length. What is the initial control that we need? We need coordinates of a station, we need the azimuth of the first line, and this is what we need for both kinds of traverses. In the link traverse, we need control at the beginning and we need control at the end. This is the end, the azimuth of the last line, and then the coordinates of a station. The solution of the traverse, that means we want to do the calculations of the easting and northing of all of these unknown stations. The circles, they represent stations of unknown coordinates, while the triangle, it symbols the control or starting control station. We have two methods of doing the calculations or the solutions or the computations of these unknown coordinates. First, we have the compass rule, and this compass rule is an old method. It is been used widely, but it is a stepwise solution. We remove the angular misclosure, calculate the azimuths, calculate the departures and latitudes, remove the linear misclosure, and etc. and etc. So it's a step by step. And most of the time, any residuals or any error translated from one step to the other will, of course, be inherited by the solution, and the final results will be affected by that. The second method, which is the least square adjustment, this is a method that has been adopted widely after the advent of computers and software. And this is computationally demanding, but all the computations, all the adjustments, they are done in one cycle. Angle adjustments, linear adjustment, they are done in one procedure, and it will produce the best results. And that's why in the traversing we will see this method, which is simple stepwise, and then we will show you how are we going to solve using the least square method. In the triangulation usually it is used for large areas or whole countries or even the world. And in the triangulation, the measurements, they are only the angles inside the triangles. So we have triangles connected to each other in different formats. We'll see that formats later, or layouts we call it. And then we measure all these angles inside the triangles. What do we need as a control? Of course, we need the coordinates of a starting station, we need the azimuth of a first line, and we need also the length of a baseline, because we do not have any distance measurements, so that's why we need a baseline. So, so three requirements: coordinates of a starting station, the length of the baseline, and the azimuth of a line. The solution, of course, of a triangulation network, as with the traverses, can be done using different methods. Over the years, this is an old methodology. Over the years, there was many methods how to try to control the errors, at the end reaching easting and northing of the unknown points in the most accurate method. So we have either we will go for solution of triangles. This is the first method. This is like calculation elaborate, and it can be done different routes and can produce different results. That's why nowadays, because of the computers and software, we use the least square adjustment, and this will take the network and adjust it at the same time. We have some more requirements for this method, is that we have to come up with the initial values of the unknown stations. So we have to come up with certain initial values of the unknown stations, while in the solution of triangles, no, we will solve for it. This is like extra work, but I think this extra work pays off in terms of accuracy and control over the solution. As we said, besides the solution of triangles and least squares, we have many other methods that they were developed over the time, but in our chapter here, in our study, we will go for least squares for doing the solutions. Preparation of the data for the least square is not that hard. At the same time, it will give you the best results without complications. Trilateration, it is one method of those classic old methods to solve for the horizontal control coordinates of the points. It is used either for small, mid, or large size areas. As we said, this is an old method, but it was not used widely because of the need to measure distances. Because in this method, we only measure distances. All the sides of the triangles, they are measured. As you can see in the here, we have all the measured distances between, and for the same as in the triangulation, we need the initial control of a coordinates of a station, azimuth of a line. We do not need a baseline, because the lines, they are all measured in the field. This is the basic measurements. In triangulation, it is the angles and only the angles. That's why we needed a baseline. But in the trilateration, we do not need a baseline as much, because all the sides are been measured. We do not measure any angles in the trilateration thing. Of course, the solution, as before, that we need to find the easting and northing of the points from the measurements of distances. And we have many methods: solution of triangles, least squares, and something else. One thing to note, that this one, before, it was not used on a large scale, because before we did not have like the best instruments to measure distances. So the distances between points, like 10 kilometers, 3, 4, 5, 10 kilometers, it was hard to measure. But when the EDMs became like total stations and electronic distance measurement machines, they are available, we started to rely on trilateration more than on triangulation. Triangulation is becoming hard to measure the distances, while the angles, while the trilateration, it was, because of the new equipment, it was easier to measure the distances. So there was advantages and disadvantages of the methods over the time, over the change of the technology. As we said before, the GPS and GNSS, which the GNSS means Global Navigation Satellite Systems, which is from different parts of the world, like the Russian, the American, the Chinese, the Japanese, the Indian ones. everyone, they have their own constellation. Some of them, they are global, some are not. But the GPS is GPS, called the Global Positioning System, and this is the American system. GNSS is the worldwide, is the umbrella for the worldwide systems. So in triangulation, we measure the angles. That meant that we needed to see the points from one to the other. To be able to measure the distance, the angles. For trilateration, it is distances. So if you want to measure a distance between one point and the other, you have to see the points. Now, the GPS or GNSS systems, no, we do not need to see the points. We will put a receiver, like the receiver you can see here. You will put it on a point, and you will put another receiver somewhere else. And we will do precise measurements of the distances without the need for points to see each other. And this is what encouraged the use of this method, especially after the development of the method and precise measurements could be achieved. And that's why triangulation and trilateration, these days, they are rarely used, while the whole thing now, it's been put on the GPS or GNS systems. But we will not say that we will not do triangulation or trilateration anymore. No. In some areas, around dams, around bridges, around some areas where local areas are affected and we need really precise measurements, we still do triangulation and trilateration on a smaller scale. We will never like ditch or just ignore the two methods completely. We will still, and we will continue to use them with the traverses as well. Now we have another method of doing the horizontal control. It's called the resection. And we have another method, we'll see it later, it's called resection. They are like a specialized form of triangulation and trilateration. So mainly resection and intersection, they are specialized form of triangulation. What do we do in these? We always have three control points, and from these control points in the resection, we will put the instrument on the unknown point. So what do we have? We have the instrument on an unknown point, and we cannot access that. We cannot put the instrument on the control points. So the control points, they are not occupied by the instrument. The total station is only installed on the unknown point. And then we will do measurements of the angles between the unknown point and the other three control points. What do we need as a first control? Of course, we need the coordinates of these three control points. So from these, the coordinates of these three control points and the measurements of the angles between the unknown point and the three control points, we can do the solution. Now the solution, again, for this method, it's like the triangulation. Either we would do it using solution of triangles or least square adjustment, or any method that we will do. The solution of triangles can produce different results from different routes, and that's why we prefer nowadays, because we have computers, we have software, we will do least square adjustment. The same as with the triangulation, we prepare the data files for the software, and we will do the solution using that software. Again, always the least square adjustment, because this is a nonlinear problems, we will always need initial values for the unknowns. What are the unknowns here? It is the coordinates of this point. Let's call it point P. So we need EP and NP. This is the final result that we want to have, which is the exact or the precise coordinates of this point. And that's why, because this is an nonlinear least squares, we have to have initial easting of the point and also initial northing of the point. So we have to come up with these initial. It doesn't have to be accurate. No, it should be like any reasonable. We'll teach you how to come up with reasonable values as a starting point. So we have to start as a starting point. The solution is iterative, and with the iterations, we will reach to the final precise measurement values of the coordinates of this point. The same thing for the intersection method. The intersection method is another specialized form of triangulation, it is the other way around. So instead of having the instruments over the unknown point is not accessible. We just have to measure. We put the instrument on the first control point, the second control point, and the third control point, and we measure angles, all right, from these. Here we have, this is one angle, and then we measure this angle, and we measure, this is another one. So we will be measuring angles from the control points to the unknown point. And this is what we have, different from the resection. The same thing, it applies. We need coordinates of 3 control points where we put the instrument, here, actually here. And so these are alpha, beta, gamma, and delta. These are the values, these are the angles that we measure in the field. We can solve using the solution of triangles again, or we use the least squares. The least squares is the best method. We will do it here. What we need, as we said, initial values for the unknown coordinates of the point P, initial coordinates, and after that we will do the least squares and we will come up with the precise coordinates of this point. The last method for doing the horizontal control network, solving them, is the GNSS centralized processing. In this chapter, we will not go for the details of this method as much. We will take a separate chapter for doing this. At the end, GNSS surveying, it is replacing all other methods because of its precision and the need not to see the points from each other. And that's why we use them. Now, another thing is that the GNSS surveying will not only produce easting and northing, it will be easting, giving you easting and northing, and let's say called the up, which is the elevations. So it's a 3-dimensional surveying. You like it or not, it is 3-dimensional. We do not have to do separate horizontal control